Last video, as an example, we use a resource allocation problem. In this session, we'll look into another frequently encountered business setting where the optimization toolkit can be used to make best decisions. In a network setting, a setting where demand and supply are spread across the network of locations, and the goal is to make sure that the demand and supply match at the lowest possible cost. Let's have a look. We use Juror for this resource allocation problem. Now in this section, we'll have a different kind of optimization problem, a problem where optimization involves a network of locations. Here's the business context we're going to analyze. Keystone Dry Goods and logistic company that moves goods for its customers. This particular customer needs a Keystone to move goods from network of locations that clients include 3 warehouses and 3 distinct centers. Here are the warehouses, here are the distribution centers. So this is the complete network. Okay, from each warehouse, Keystone must transfer out a certain amount of powdered drink. For example, out of Chicago warehouse, it must move exactly 20 tons. So here's an illustration of what must be shipped out. 15 tons out of Los Angeles, 20 tons out of Chicago, and 30 tons out of New York City. Each distribution center has a minimum requirement for the amount it must receive. For example, at least 10 tons must be received by the Denver distribution center. And here's a picture illustrating these 2 types of requirements. Requirements are exact amounts that must be shipped out of warehouses, and the minimum requirements for the amounts to be shipped to the distribution centers. Now, shipping is costly. Here are the costs that Keystone will incur when shipping 1 ton of powdered drink from each warehouse to the other distribution center. For example, if it tries to ship 10 tons from New York to Austin, it will incur a shipping cost of $132 for each ton, and the total cost will be 132 times 10, 1,320. So here's the problem Keystone is trying to solve. It is trying to find out the cheapest way to transport the goods, while making sure that certain amounts are moved from warehouses and some minimum amounts are delivered to each distribution center. So let's cast this problem formulation into 3 pieces. What kind of decision must Keystone make? The amount to ship from each warehouse to another warehouse distribution center. What objective does Keystone have? It wants to minimize the shipping cost. What kind of constraint does it face? There are supply constraints at the warehouses and the demand constraint at the distribution centers. We can specify decision variables, objective functions, and constraints. Let's start with the decision variables. The company needs to determine how much to ship from each warehouse, like Los Angeles, Chicago, and New York, to each distribution center. Denver, Washington, D.C., and Austin. So let's assign a variable XLD to stand for the amount sent from Los Angeles to Denver, and another one to describe the amount shipped from Los Angeles to Austin. And the third one to denote the amount shipped from Los Angeles to Washington, D.C. Let's add 3 more variables to designate shipments from Chicago to Denver, Austin, and Washington, D.C. And let's do the same for the shipments from New York to Denver, Austin, and Washington, D.C. So we have 3 plus 3 plus 3, 9 decision variables. So what about the objective? Keystone tries to select the decision variable so that the total shipping cost is as small as possible. So if I try to ship XLD tons from Los Angeles to Denver, what are the cost implications? Okay, I ship from Los Angeles to Denver, and it will cost me 105 per ton. So shipping XLD tons from Los Angeles to Denver creates a cost contribution of 105 times XLD. And shipping XLA tons from Los Angeles to Austin creates a shipping contribution of 135 times XLA. In the same way, shipping XLW turns from Los Angeles to Washington, D.C. creates a cost contribution of 153 times XLA. So the objective function has three contributions from shipments in Los Angeles, three more from that originates from Chicago, and three more from shipments that come from New York. Now the objective function must be minimized in the presence of supply constraints in the warehouse and demand constraint in the distribution centers. So okay, here's a reminder of what the supply constraints are. Keystone must ship exact amounts from each warehouse. For example, all shipments from Los Angeles to Denver or DC or Austin must stand up to add up to 15 tons. So the supply constraint for Los Angeles warehouse looks like this. XLD plus XLA plus XLW equals to 30. Finally, all shipments from New York must add up to 30. So to summarize, we have a supply constraint for Los Angeles, Chicago, and New York. What about the demand constraint? Here's a reminder for what the requirements for each distribution center are. Let's start with the Denver distribution center. Denver must receive at least 10 tons. So here's how the constraints will look like. And the Austin center must receive at least 13 tons. Finally, the Washington, D.C. center must receive at least 20 tons. Here's a summary of demand constraints. We have one for Denver, one for Austin, and one for DC. To put all together, we have an algebraic model with 9 variables, and we have expressed the objective function, the total shipping cost, in terms of these 9 variables. We have put together expression for supply constraints and the demand constraints. We also must ensure that the shipping quantities are non-negative. Now, we do not have to restrict the shipping quantities to integer values, since it's possible to ship fractional amounts like 12.5. Now we have to formulate an algebraic model for the keystone problem. We can go to Excel, set up the spreadsheet formulation for this model, and find the optimal shipping plan using Solver. Let's do it now. We have prepared the keystone 0. Go ahead and follow the steps. We go through and here's the Excel template. As you can see, the spreadsheet contains the data for the keystone example. None of the formulas. We'll use the algebraic optimization that we made earlier. Convert step by step in the solver form. We'll define on the spreadsheet 3 components of the optimization model: decision variables, objective functions, and constraints. Let's start with the decision variables. In this problem, the decision variables are the amount of powdered drink to ship from each warehouse and to each distribution center. There are 3 warehouses and 3 distribution centers, so we have 9 decision variables. In our template, we have 9 cells, B12 through D. The value of these decision variables, like we did in the Judah example, let's put some trial values in these cells, say 10 in each of them. Okay, shipping from Los Angeles to Denver is 10, and all of it is 10. 10 times 9 from B12 all the way through each one. Each warehouse to each distribution center, again, this is not feasible. For example, LA warehouse would need to ship out 30 tons, and it has only 15, but that's okay for now. Those numbers we have put in there, decision variables, the solver will come up with the optimal numbers anyway. Okay, we have defined the decision variable cells. Let's color them into blue and make the font bold, just like we did earlier. Next, the objective function cell. In this example, the objective function is the total shipping cost, and we would like to minimize this objective. So let the template as the template, the F3 is where the objective function we're going to put. How do we calculate the total objective of shipping cost? Right. We should multiply each of the 9 shipping quantities by the corresponding shipping cost from the cells B6 through D8 and add those 9 products. Like this all sounds like the sum product of our decision variables and the corresponding cost values. Let's see how we can use the sum product formula in this case. In cell F3, we type sum product of our decision variables B12 through D14 and the corresponding cost values B6 through D8. The result is, according to Excel, 11,570. So we have the objective function cell. Let's change the font bold and red just like we did in Juder case. Now we move to the constraints. In the keystone problem, there are 6 main constraints. 3 supply constraints, 1 for each warehouse, and 3 minimum demand constraints, 1 for each distribution center. Let's start with the supply constraint. The first supply constraint states that the total amount shipped from the LA warehouse must be exactly equal to 15 tons. Let's go to the cell E12 and calculate the total amount shipped from LA warehouse under our trial shipping, and we need to sum the shipping amount from LA warehouse to each distribution center. We will put together the sum B12 shipped to Denver, C12 Austin, D12 Washington. We sum them all up. The result is 30 tons. Again, we can do the same calculation for the remaining 2 warehouses. We just copy and paste the formula in cell E12 to the cells E13 and E14. Now you can see under the trial shipping plan we are considering the amount shipped from each warehouse is 30, and that is certainly not feasible, but let's worry about this later. Now we deal with the minimum demand constraints. For each distribution center, there's a minimum amount that it must receive. Let's start with the Denver distribution center, and let's calculate the cell B15, the total amount this distribution will receive under the current shipping plan. We are summing the shipping quantities that go to Denver from each warehouse. Sum of B12, B13, and B14. And the answer is 30 tons. We can do the same calculation for the remaining 2 distribution centers. All we have to do is copy and paste the formula in B15 to cells C15 and D15. This, for example, now we have what we have now in D15. It sums of the shipping quantities that go from Washington to LA, Chicago, and New York City. We have specified the decision variables, the objective function, and the constraints, and we are ready to call the solver. We go to Data, click on Solver. Let's first show the solver where the objective is. It's in cell F3. At this time, we would like to minimize that function. In other words, we'd like to make the shipping cost as small as possible. Next, we specify where our decision variable is. They are located in cells B12 through D14. Finally, the constraints. The supply constraints state that whatever amount which has to ship, the total shipping amount from each warehouse must be exactly equal to the amount we have specified. So we click Add and tell the solver that the number is in the cells E12 through E14 must be exactly equal to the numbers in the cells G12 through G14. The minimum demand constraint states that each distribution center cannot get less than what is required. Thus, we click add again and state that numbers in B12 to D15 must be greater than or equal to the sum specified in cells B17 to D17. We do not need to specify that the shipping amounts are integer. We can ship 9.4 tons between a particular warehouse and a particular distribution center if we choose to, which have the non-negativity of the distance variable selection. We leave the solver method as it is, the GRG now linear, GRG linear, non-linear, and we say solve. Here's our optimal solution. Here's the picture of the optimized spreadsheet, and you can see the lowest cost that can be achieved here is $7,485. Solver is a useful tool for learning the optimization techniques using problems with small numbers of variables and constraints. However, the real size problem represents a serious challenge for the solver. Fortunately, there's a number of commercially available optimization tools that can tackle large problems. The good news is that whether you are using a solver or a commercial tool, you will still have to work with decision variables, objective function, and constraints. Here's a link to a recently compiled list of commercial optimization tools. A journal called Interfaces publishes articles on actual business applications on analytical techniques. Interfaces articles is a great source of practical knowledge on how to identify analytical opportunities, how to build models, and how to implement them. We have picked two examples. The first article is about optimization of profits and Chevron, one of the world's largest integrated energy company. The second is about applying analytical tools, including optimization, in one of the world's leading fashion retailer, Zara. Please keep in mind that in practice, analytical projects may often involve multiple analytical tools. In particular, optimization will be needed to be combined with descriptive and predictive analytical tools like forecasting.